Hello friends, welcome to EC Academy.
In this lecture, let us understand transient analysis. Here, we'll understand the circuit behavior at t is equal to 0. Usually, when we look at the circuit, we analyze them as a steady state where everything is calm and constant. But in real world, things change, switches flip, components fail and power fluctuate. Then the circuit will switches from one state to another steady state, and this transition from one steady state to another steady state is known as the transient state. Now let us understand the steady state versus the transient state. On the left hand side, we have written the steady state. In DC or AC analysis, the current and voltage are having constant amplitude. On the right hand side, we have the transient state, which is the bridge between one steady state and another steady state. Because the energy stored in the elements like capacitor and inductor cannot accept or release energy instantaneously. There is a delay. Hence, the circuit need some transient time to move from one state to another state. Now let us understand the physics of switching. To analyze the transient analysis, let us look at this timeline. So in the timeline, at t is equal to 0 is known as the switching event. Mathematically, we can distinguish between two specific instants like t is equal to 0 minus, which is initial condition. It is the instant immediately prior to switching. And we have t is equal to 0 plus, which is the instant immediately after switching. So there is a strict rule. We must separate what's happening before switch from what happening after the switch. Now let us understand the component personalities. Here we'll understand how do our components react to the shock or to the switching. First we have a resistor which is realistic. It adopts instantaneously. The voltage follows the current immediately in the resistor. The inductor is a stubborn one. If we say stubborn, which means it refuses the sudden change in the current. If 2 ampere were flowing before the switching, 2 ampere must flow immediately after switching. That is the personality of inductor. If we take capacitor, it is known as the preserver. It refuses to sudden change in voltage. It tries to maintain potential across the terminal during the switching. Now let us understand the equivalent circuit for each component. Here you need to remember the resistor doesn't have any change at t is equal to 0 plus, which means immediately after switching there will be no change across the resistor. An uncharged inductor where I is equal to 0 acts like a open circuit because it will not allow the current to flow instantaneously. The uncharged capacitor where V is equal to 0 acts as a short circuit because it holds the voltage at 0. If the inductor and capacitor have already charges like I is equal to 0 for inductor, we can model them as current for charged inductor and for charged capacitor where V is equal to V naught, we can model it as voltage source. So these two represents the charge storage or storage of energy. Now let us understand the inductive response with series resistor and inductor. Let us consider a series RL circuit. When we close the switch, the inductor opposes the rise in current as we have understood the property of inductor. Now, for this circuit, if we apply KVL, we will get V is equal to Ri plus L di by dt. If we rearrange the above equation, we'll get di by dt plus r by L into I will be equal to V by L. So here we have divided this equation by L. So to obtain this equation. So in this equation, L di by dt represents the voltage drop due to inductor opposing the rise in current. Now let us understand the exponential rise. If we solve this differential equation, we will get the equation for current as I of t is equal to V by R into 1 minus exponential to the power of minus R by L into t. So in this equation, L by R represents time constant tau that determines the speed of transient. So from this, we can understand that current doesn't jump straight up. It rises exponentially as shown in this figure. Now let us understand the capacitive response where we are connecting series RC in the circuit. So let us consider the circuit where R and C are connected in series. So here you need to remember that the capacitor acts as a short circuit initially. This means at the very first moment it draws maximum current. As charge accumulates, the capacitor voltage rises to oppose the source and the current start dropping. So for inductor, current start increasing, and when the capacitor is connected, the current start dropping because it opposes the rise in current. So if we apply KVL, we can write V is equal to Ri plus 1 by C integration of I and dt. If we differentiate this equation to remove the integration, we'll get 0 is equal to R di by dt plus I by C. So this is the current equation for the RC circuit where I of t is equal to V by R exponential to the power of minus t by RC. And this is the voltage equation. For RC circuit, the time constant tau will be R into C. Due to this equation, it results in exponential decay of the current. The current initially starts at V by R and it crashes down towards 0 as shown in this figure. So at one time constant, the current has decayed to 36.8% of the initial maximum value. Now let us understand the S domain, which is very important in a transient analysis. For simple circuits, we'll use the differential equations, but for complex network, we use the S domain, which turns the calculus into algebra. In time domain, we represent resistor as R, inductor as L, and capacitor as C, and source voltage as V. So for this, if we apply Laplace transform, we'll get the terms in S domain where resistor remains as it is, it will be R. The inductor becomes impedance, that is represented by SL. Capacitor becomes impedance, that is represented by 1 by SC, and the voltage will be V by S. So this allows us to solve the current equation I of S is equal to V by S divided by R plus SL by using basic algebra. So this shows the steps that is used solving the equation in S domain. First, we'll go with the equation which is obtained using S domain. For this, we'll apply the partial fraction. Then, we'll take the inverse Laplace transform to get back the time domain result. So this result match our differential equation solution exactly. So from time domain, we'll convert to S domain using Laplace transform. Then after calculations, we'll apply inverse Laplace transform to obtain the time domain equation. Now let us see the summary of transient analysis protocol. So here is the protocol for solving any transient problem. First, the status Q, which is t is equal to 0 minus. Here, first we need to find the initial current in inductor and also voltage across the capacitor. So here, to solve, we need to remember that the inductors are short circuited, capacitors are open circuited, then we can find the initial current or voltages. Then the instant where t is equal to 0 plus, we need to draw the equivalent circuit by replacing inductor with current source, capacitor with voltage source. Then we use initial values where we'll apply KVL or KCL to find I0 plus and derivatives. Then the response where t greater than 0. Here we'll use time constant tau for simple circuit or Laplace transform S domain for complex network. So finally, we can say the transient analysis is the study of how the system stabilizes, whether it is a power grid or a microchip. Understanding the moment t is equal to 0 ensures our design survive the shock of the real world. This is about the transient analysis. Hope you have understood the topic. Thank you.